Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today session we're going to continue talking about material response to electrostatic field. This is mentioned in our textbook, Sadiku, in chapter 5. Okay, so as what we have seen before, shown here, the schedule that we are planning in learning about material influenced by electrostatic field. So from the shown diagram here, we have completed two main topics, which are current, and then we talk about conductor. So we have completed those. So in this session, what we're going to do, we're going to talk about dielectrics. Okay, so about dielectric, and we know dielectric material in terms of behavior or electrical behavior is totally opposite to conductor material. So we're going to talk about two main issues. The first one will be known as dielectric under static condition. Okay, and then we're going to follow with dielectric boundary condition. So that should be the main issue that we're going to discuss in this particular session. Okay, so without further ado, we're going to talk about the first issue, dielectric under static conditions. Okay, that should be our interest now, dielectric under static condition. Okay, that should be our topic. I'm sure you have seen the same topic shown before, but in previous discussion, we focus on material which is known as conductor. So what we talked about before, conductor under static condition. So I'm sure you can visualize what is our intention in this particular discussion. Is quite similar to the one we have seen before, but the only difference is the material of interest. Before we talk about conductor, but in this particular session, we're going to discuss about dielectric. So let's redraw that simple diagram. So what we need to have in our discussions, the first component should be the material, and then we're going to denote the material here as dielectric. Okay, and then the second component needed in the discussion should be the applied field. And since we are still in the world of electrostatic, so we're going to assume, or we're going to let the field of interest here to be electric field. So we're going to call it as applied electric field. So that should be the second important parameter. Okay, and then the third parameter should be the charged particle. Okay, so that should be what we denote to be rho v. How the charged particle respond to the applied field. And we have seen in conductor, the rho v going to be diminished, meaning that when the applied field applied to the material, there is no more volume charge. In other words, volume charge in a conductor exposed to electric field will be equal to 0. So let's talk about what happened to the rho v, the volume charge density, in a dielectric when exposed to applied electric field. So that should be our interest now. So recall the equation that we derived together. Okay, recall our equations rho v. Remember the equation that we derived together from the continuity current equation model. What is it? Rho v equal to rho v naught exponential minus, what is it? sigma over epsilon naught T. Remember the equation that we derived together, and we managed to solve that equation. So that should be the solution. So this rho V is actually this rho V. And rho V naught is our initial value. See? So what we said now, at T equal to 0, meaning that the time T equal to 0, before the material been exposed to electrostatic, the rho V is equal to rho V naught. That should be the assumption that we used before in the discussion, meaning that there are volume charge. So now let's draw the graph that we're going to refer now. So our graph that we're going to draw now will be rho V against time. Okay, so that should be our graph. So this graph refer to where in our diagram, model diagram, refer to this position. Okay, and then we said that before the dielectric being exposed to electric field, the value of our rho V is known to be rho V naught. That's what we assume. So now, what we're going to do, we're going to use this particular equation to model what happened to the charge rho V as the dielectric going to be exposed to electric field. So what we're going to conclude, or we're going to say now, for dielectric, okay, what is the value of our sigma? Sigma usually very small, or sometimes we can call it to be equal to 0, very good dielectric, or we can assume to be very small. Okay, what happened to the equation? So what we're going to see now, when sigma is very small, so the term that you're going to have here, very small number. So when we increase the t, so meaning that when we apply, so we are saying here, t greater than 0, E applied will be not equal to 0. That's what our condition now. What we are doing now, we are exposing the dielectric with electric field. So what happened to this particular equation in terms of graph? What we're going to see is nearly stay flat. Okay, so that's happened for dielectric material, whereby in our conductor, the rho V immediately becoming 0 because the sigma value is very, very large. Okay, so that's going to, so meaning that we're going to assume in this case the rho V remain the same. It does not affect so much due to the existence of the E applied to the dielectric material. So now the issue here, we're going to re-explain using a different approach than what we have done in our conductor. So what I'm going to do now, I'm going to try to explain what happened to the charge, because we know the charge is going to be there, it's not going to be becoming 0, so it's going to be still there. So the way we're going to discuss about this rho V, the charge that is still at this position even though we apply electric field, we're going to have two version of discussion. So two view of discussion. So I'm going to recall the first discussion in terms of what happened to the charge is by talking about in terms of microscopic view. Okay, microscopic view, in other words, is an atom, one atom. So what happened to one atom of dielectric when exposed to the E applied? Okay, that's what we're going to talk about, because we know the charge still stay at that position, because from this particular graph we conclude that the charge still there because the value of rho V nearly remain the same even though we expose the dielectric material with electric applied. So now we're going to talk about in terms of one atom. What happened to one atom dielectric when we expose to E apply, and that particular discussion we're going to note as microscopic view. So an atom, how it responds to E applied. So to talk about that idea, we're going to refer to what is known as Bohr's atom diagram. Okay, so we're going to recall an atom. How we represent an atom, but we are going to use what is known as Bohr's model. Okay, and then we know that in terms of atom, as what you have learned in physics and other subject, atom can be divided into two main components. The first component going to be nucleus. Okay, and then nucleus will contain a lot of positive charge. Okay, that should be our nucleus. And then surrounding the nucleus will be orbit, and residing in this orbit will be electron. So I'm going to draw electron with charge negative. So, and then this electron can move freely within the orbit, whereby the nucleus will remain stationary. So that's typical model of an atom postulated by Bohr, and we use a lot in discussing about atom using this particular model. So that should be the condition of the atom when we state here E applied is equal to 0. Okay, meaning that this is the condition of an atom that does not being exposed to any applied electric field. So that should be the norm model of an atom mentioned by Bohr. So now we're going to introduce electric field. So I'm going to introduce electric field. So now we're going to assume our electric field similar to the above direction, showing upward. So this should be our E applied. So now the E applied is not equal to 0. So meaning that something will happen in the atom. So let's talk about that. So what will happen in terms of the actual structure? The nucleus will be the same because very large, and then the orbit still there. Okay, so that's actually the structure of the atom. But the only difference here, the electron will be forced to be appear to be in this particular position. So all the electron now, okay, gather together at the entrance where the electric field is being introduced to the atom. So you have one location filled with a positive charge, another location will be filled with negative charge. You meaning that, in other words, they got two distinct group of charges in the atom. So let's see, if I apply the electric field from left to right, the electron will gather together on this left position of the atom. If I'm applying the electric field from top to bottom, the electron will be gathered together at the top part of the atom. So meaning that where the position of the electron will be depend on how you apply the electric field to that given atom. Okay, so now, so we're going to redraw equivalent diagram now. So to make it simple, so what we're going to do, we're going to redraw it, meaning that represent using a simple model diagram. So we can state that the nucleus is going to be filled with positive Q. So this atom actually representing this particular nucleus, whereby the electron will be represented by another atom charge. I'm going to put it as negative Q. And then the distance between these two charges, we're going to denote as vector D. So that's how we represent, make it simple version of our diagram. This is just equivalent. So we can make it simplified further. So I'm going to simplify it further by representing this particular behavior with just one line of vector. Okay, and this vector we're going to denote as small p, and this small p in terms of equation will be equal to the charge, so Q, one of it, and then multiply with the vector D. Okay, that should be the equation representing the P, which is now the simplified version of this structure, the behavior pattern that we seen here. And this small p, we're going to call it to be known as electric dipole moment. Okay, there's a name for P, so we call it electric dipole moment. So that should be the name to our P. So in other words, when an atom been introduced to electric field, we're going to have a vector component known as small p, and that small p we call it to be electric dipole moment. So as a conclusion, electric dipole moment will exist in an atom of dielectric material when we expose that material to electric field. Okay, so that's going to be the pattern of an atom, or we call it to be the outcome of the microscopic view discussions. So what we're going to extend this idea further, we're going to talk about what happens when you have a group of atoms now. So we're going to re-explain it, okay, by what we know as macroscopic view. So we're going to call it as group of atoms. So that should be the logical step we're going to do. So meaning what happened to the group of atoms. So let's say this is the structure that we have. Okay, this is the dielectric material. Initially, when E applied 0, so what we're going to say, nothing happened. In terms of individual atom, just remain as it is. Therefore, even though you have a group of atoms, still nothing happened because nothing happened to those atoms when you does not apply E field to that given dielectric material. Okay, for this discussion now, let's say let the number of atoms in our model n, let's say make it equal to 4. Actually, there are million of the atom number, but for the sake of discussion and make our diagram a bit easier to be understood, let's say the number of atoms in the discussion here is equal to 4. And then we have the dielectric material, same structure. But now we're going to have electric field. So let's show the direction of electric field as similar to the above direction. So this should be our E applied, which is not equal to 0. So what's going to happen then? First, we're going to introduce, in terms of individual atom, we're going to create electric dipole moment. That's one aspect of the behavior. Then what happened? All the atoms that exist in this dielectric world have the same behavior. They're all becoming, or they're all producing their own electric dipole moment. So meaning that if you have 4 atoms, you're going to have 4 electric dipole moment in your model. So meaning all the electric dipole moment will be a small vector showing in the same direction. The direction will be directly dependent on the E applied. Okay, if the E applied showing upward, all the electric dipole moment that appear to be created in the dielectric material also going to show upward. So now you're going to have some sort of the sum of small vector. So if I sum all these small vectors together, I'm going to reintroduce new parameter now. We call it capital P. Okay, the capital P in terms of mathematics, we can denote it to be equal to, okay, so the sum of, so we're going to call it limit, depending on the volume, tend to 0. And then you need to sum all the Pi that you have, divide with the delta V. And then the number here, n, or I equal to 1 to 4. So that should be the equation that we're going to create for this model. So meaning that in simple word, all these small pi will sum together, and then that summation of small pi will introduce a new parameter. And this new parameter is represented in capital P, totally different than the above parameter symbol here. This is in the small p. So this new parameter, we call it to be known as polarization vector. Okay, so for this case, we know that this value, the capital P, will not equal to 0. Because from the diagram we can see, they are all the small p are in the same direction, therefore they're going to contribute to the appearance of the polarization vector. Whereby in the original dielectric, since there's no small p, so the sum of all these will be p equal to 0. So capital P now will be equal to 0 for the unexposed dielectric material, whereby the dielectric material that exposed to the electric field going to produce what we call it to be polarization vector. It's not equal to 0. So due to that reason, we're going to name this dielectric material on the right as polarized dielectric material. Okay, so that's the name given to the second condition of dielectric material. It's been polarized, so we call it polarized dielectric material, whereby for the original dielectric material we call it unpolarized dielectric material. Unpolarized dielectric material. Okay, so that should be the conclusion in terms of macroscopic point of view. A new parameter, we're going to denote that to be known as polarization vector. Okay, so now you can see what it meant by polarized dielectric material and unpolarized dielectric material. So now, since what we can see here, the P in this particular model will be not equal to 0 whenever the dielectric material is exposed to the E applied. So the condition of P, or the capital P, to exist is affected by the appearance of E applied. So what we can state that, how we going to relate the polarization vector to the electric field. So what we can conclude, or we can state now, the P, which is polarization vector, is equal to, we're going to introduce a constant here known as electric susceptibility, epsilon naught multiplied with E. That should be the equation that relating the electric field to the P, because we know the P only appear to be in our discussion when the E applied is not equal to 0. So I'm going to write in terms of word now what is this term. So we call it to be electric susceptibility. So this parameter is actually mentioning how the material respond to the electric. It's a measure of how easy the material respond to electric field, meaning that some material do have difficulty for E and P to be coexistent, but in some dielectric material is much easier. So this is a measure of that pattern, how that material respond to the electric field. We call it to be known as electric susceptibility. Okay, so that should be the equation that we're going to end regarding macroscopic point of view. So then what will happen to the discussion? So what we're going to do, we're going to summarize what we have done so far. So what we are saying now, so when dielectric material, okay, exposed to electric field, E applied, we're going to produce what is known as polarization vector. Okay. So now what will be created by this appearance of polarization vector? So that should be the next issue of discussion. What's going to be created when you have a dielectric material being polarized? So with that, I'm going to introduce to you the charge due to P. So we're going to introduce charge. Okay, charges due to P. So meaning that, in other words, when the dielectric material been exposed to electric field, is going to introduce polarization vector. So that polarization vector will introduce new charges in the dielectric material. So that should be the conclusion, but let's explain that in much more detail here. So let's recall, you have a dielectric material that we're going to draw now in 3D. So I want to make it big now so that you can see this idea easily. So let's draw our dielectric material. So it's a red box here. Okay. And then let's see our E applied given to this particular dielectric material is as before, from bottom to top. So that should be E applied. So now what we're going to see inside this dielectric material, the arrangement of all the dipole moment. What you're going to have, you're going to have positive atom linked to the negative group atom. You're going to have all this electric dipole moment structure distributed inside this dielectric material. So this should be the conditions that what happened in the dielectric when you expose to E applied. So that's going to be extended. Let's say I'm going to represent this positive, this negative. You're going to have positive, negative. So positive, negative. So let's draw everywhere. So here should be positive, negative. And then here should be positive, negative. So all of this region is filled with this electric dipole moment. Okay. So now let's focus our view on the top surface of this dielectric material. What you're going to see up here? You're going to see there's a layer of positive charge, correct? So meaning that appear to us on the top surface of this dielectric material is filled with one type of charge that is known as positive charge. And therefore, we're going to call this to be surface charge. Okay, and we know that surface charge should be represented by symbol rho s, correct? So rho s is known as surface charge density. But when you look further into this particular diagram, this positive charge is not free charge. As you can see, it's bounded to the negative charge here. So it's not free. Is bounded, even though the top layer is filled with positive charge, yet this positive charge not freely move. Those charges are bounded to the atom. So therefore, we have to rename that to make it clearly different than the one that we talked before, the surface charge density. But now we're going to add the symbol B. So we call this one bounded surface charge density. Yeah? Bounded surface charge density. Okay, because you can see there's a surface charge, but yet is bounded. Similarly, if you look at the bottom surface of this dielectric, you can see that this particular surface will be filled with what? Positive or negative charge? Yes, negative charge. So we're going to call negative rho SB. Okay, so that should be the first type of charge that going to be introduced in the dielectric material when that dielectric material be exposed to E applied. So therefore, we're going to see this rho SB will only exist when there is a polarization vector. Without any polarization vector, let's say polarization vector is equal to 0, the rho SB will becoming 0. When the polarization vector is not equal to 0, then only the rho SB will not equal to 0. In other words, this rho SB is affected by the polarization vector. So in terms of equation, we can relate those two together using this model mathematics. Polarization vector dot with a n. Okay, so let's make it a bit easier to be understood. So let's give access to our model now. So let's give this particular side of the dielectric as x-axis. So this particular side is our y-axis and the vertical direction to be our z-axis. Okay, so what we can see now, okay, in this particular model, we can see the E, okay, the E in which component now? Which particular axis that you can represent the E? Good, the E can be represented in the Z direction. Do we agree? So we need that the E is parallel to the Z direction. So we're going to say that the E actually equal to the magnitude of E in terms of Z direction in the Z direction, because the X component and the Y component of the E is not exist here since the E shown as such. So due to the behavior equation that we see here, so we can conclude the P, okay, going to have its own solution now in which particular component the P now going to be presented. We don't talk in terms of actual, in terms of magnitude here. I'm going to present P in which particular component? Yes, Z as well. Okay, that's good. So let's say this is our surface number 1. Okay, refer to surface number 1. Okay, surface 1 now. So let's calculate the rho SB. So rho SB1, so we're going to refer to surface number 1, will be equal to the P. The P is the P in the dielectric, so we're going to put as PZ directions and Z directions dot with AN. How are we going to represent the AN? AN is unit vector. The unit vector must be away from the dielectric. So now what we're going to see, the dielectric is located in the lower region. So in terms of unit vector away from the dielectric, the AN here should be shown upward, correct? Because dielectric is down here. AN normal to this particular surface and away from the dielectric, therefore the AN here should be Z. So in other words, what you're going to have here, positive charge. Is it correct? What we're going to see here, positive charge, correct? Good. So let's take another area for sake of discussion. Let's say the surface at the bottom, we're going to denote as surface number 2. Yeah? Okay, for surface number 2, what we're going to see, rho SB2 should be equal to the same formula that I'm going to use here. So P should be still P Z in Z direction. That's what the P that exists in this dielectric. But the AN, remember, the AN should be normal to the boundary, normal to the surface, but yet the direction must be away from the dielectric. So away at this particular surface should be showing downward, correct? Because the dielectric is now located in the upper region. So now away should be negative Z. So therefore should be end with negative solution. That's why you can see this bottom region is represented by negative value. So now let's try the last surface now, this particular side area here, surface number 3, for the sake of this guy, to make it complete now. Yeah? For surface number 3. So what we're going to say now, rho SB3. should be equal to the P still the same because the same polarization vector exists in the dielectric. But now AN should be unit vector normal to the surface 3 but showing away from the dielectric. So what it means here, showing away should be in y directions. Now if you do dot product z dot y, the final result will be 0, and you see at that side there's no surface charge bounded appear in that model. Okay, in other words, the way we calculate the surface bound charge by using this equation. Okay, that should be the first type of charge being introduced when the dielectric exposed to electric field. The second type of charge that you're going to have actually exists inside this particular dielectric material. So we're going to represent the charge now. Because it's located inside the dielectric, we're going to call it as volume charge. Okay, but still the same pattern applicable as what you've seen before in the surface bound charge scenario. That behavior still applicable to the volume charge because the charge are not freely moved. They are bounded to the atomic structure. So we're going to denote that to be bounded volume charge density. So rho VB. And the way we're going to calculate this particular volume charge density, still depending on the polarization vector, but we're going to use the divergence model. Yeah? So this should be the equation that we use to calculate volume, bounded volume charge density. Yeah? So therefore, two new charges going to be introduced in the dielectric material. First type of charge going to be appear on the surface of the dielectric material. The way we calculate that particular surface bound charge is by utilizing the equation shown here. And the second type of charge that going to be introduced is known as volume charge, but we call it to be bounded volume charge density that actually appear inside the dielectric material. And then the way we able to determine the value of those volume bound charge bounded by using the second shown equation. So this just using the divergence model that we have used before when we talk about Maxwell equation number 1 or Gauss law. So it's just repetitive, repeating the same approach using divergence model, but the only different, you must don't forget to include this negative direction or negative sign in your solution. Okay, that should be the effects of the discussion. So let's recap what we have done. So we have talked about electric applied, okay, exposed to dielectric material that we're going to introduce. The first important parameter, we call it polarization vector. So this particular polarization vector will introduce two types of charges, a volume and surface bound charge. So that should be the sequence of the flow of issue regarding dielectric exposed to electric field. So now we're going to continue the discussion now. We're going to talk about the feedback effects now. So what happened to the E applied when you introduce the charge now? So since the charge been created, so the appearance of these charges, how does this new charges going to influence the E applied that produce the charges? So that should be the next issue of discussion. It's a feedback issue. So that's the norm thing in engineering when you produce something. So those something going to affect the original component that producing that something. So that is called feedback effects. So that's what going to be the issue that we're going to discuss in this the next particular session or So let's talk about that. So to talk about the effects of the charge to the E applied, so we have to use a standard equation. We call it Maxwell equation. So let's recall that equation. So recall Maxwell equation number 1. So that should be the norm in EMT. When we want to talk something new, we always discuss based on something that fundamental, and Maxwell equations are fundamental in the world of electromagnetic. So that's what I use this approach in my discussion, because I'm using something that fundamental. Okay, so remember the equation of Maxwell number 1? Yes, I'm sure most of you still remember. So we said that the divergence of D is equal to rho V, correct? And then when we talk about this equation, the medium of interest, the medium that we are discussing this equation is known as free space. Do we agree? So let's say we talk about this equation in the world of free space. Okay, and then we know in the world of free space, this equation can be modified further to become divergence of epsilon naught E should be equal to rho V. Okay, that should be our standard equation that we seen when we are still in the world of free space. So that should be what we seen before. So now we're going to talk about, now our discussion now have changed from free space medium to dielectric medium. So now we are migrating the discussion from free space to dielectric. Okay, so that's what happening now. We are changing the paradigm, the platform of medium, free space. Now we are talking about more practical material, dielectric. So what happened to Maxwell equation when you migrating from free space to dielectric? Okay, so what we can conclude, in the dielectric medium, there are two types of volume charge. The first one is the normal volume charge that we seen before in the free space medium. But especially for dielectric, there's a new volume charge that we been introduced just now, that we call it to be bounded volume charge. Now we're going to represent there are two types of volume charges in dielectric. One is the normal volume charge that we saw in the world of dielectric, in the free space medium. But now, since we just learned about the new volume charge, we're going to add that in terms of our equation, because that should be the logical step to add that in our discussion. But yet, regarding the left-hand side, we're going to make it the same, because we don't have any knowledge regarding this issue. Just leave it as it is. Okay, so that should be our new proposal of Maxwell equation in dielectric, taking into account the issue that we just discussed, especially what? The introducing of volume charge known as bounded volume charge that we talked about just now. And from the equation shown just now, this particular term can be substituted with negative divergence of P. Okay? And then when we rearrange the mathematics now, if we shift the term here to the right, what we're going to have now, we're going to have divergence epsilon naught E plus P should be equal to 0. That should be new arrangement of the equations. And then remember, Maxwell equation actually presented by this equation should be applicable in any medium. So meaning what? If I'm talking about free space medium, the Maxwell should be presented by this equation. If I'm talking about Maxwell number 1 equation in dielectric medium, this Maxwell equation must be still the same. So meaning that this pattern of Maxwell equation must be the same regardless any material. So to have that, so you have to make sure now we're going to compare the general equation to what we just developed just now. So what we're going to state now, the D, okay, in dielectric material should be equal to epsilon naught E plus P. Okay, so that's a new equation that you're going to have, because now since dielectric material do have polarization vector, so this equation must be used to represent dielectric material. For free space, we know that the polarization vector is equal to 0, so this D equal to epsilon naught E is going back to the original version that we stated before. But when you talk about dielectric, the polarization is going to be included in the equation. Okay, so therefore, how we determine the P? The P can be obtained when we know about the D, and we also know about the E. So now, for us to obtain P, the P now is actually equal to D minus epsilon naught E. So very important, because when you want to find rho SB, remember we need to know the P. So therefore, by knowing the P, then only we able to calculate rho SB. And also by knowing the P, we'll be able to calculate rho VB. So how we obtain the P? Please use this equation. Because the D, we can obtain using Coulomb or Gauss law. The E also we can obtain using Coulomb or Gauss law. So therefore, the P can be determined from this equation. So I'm going to change again the equation slightly to one that we are familiar. We already know that the P that we state before, okay, the P actually we state equal to what with regards to E is equal to electric susceptibility epsilon naught multiplied with the E. Remember the equation that we introduced earlier when we talk about polarized dielectric material? So let's substitute P with this term now. So what we're going to have, okay, so what we're going to have by substituting that, so D now equal to epsilon naught 1 plus electric susceptibility multiplied with the E. So that should be the consequence. Okay, and then this can be simplified further by saying that equal to epsilon naught epsilon R E. Okay, that should be the one you always you have seen before when you learn about physics, dielectric material. So this should be a standard formula, and the name given to this new constant, we're going to call this as dielectric constant. Dielectric constant, or sometimes we also call it as relative permittivity. There are two names to it. So, meaning that as a conclusion, when a dielectric material exposed to E applied, so you're going to create polarization. So this polarization going to be the next step going to produce charges, rho SB and rho VB. So all this behavior that we see throughout the discussion is being concluded by this term dielectric constant. So dielectric constant is the summary, or as a conclusion, how the given dielectric material respond to the electric field. Okay, so that should be our conclusion as well. The dielectric constant is the value that shown or that conclude how the given dielectric material respond to the electric field. So therefore, if you refer to handout number 8, the one that I already upload in our e-learning, if you open to page number 4, you're going to see this table given. Okay, this table shown material relative permittivity. And what we can see now, there are various value of dielectric permittivity or dielectric constant shown here. Okay, the value indicates something. As a simple conclusion, it meant how that given dielectric material respond to the electric field. Okay, so that should be what you're going to conclude now. The higher the value of relative permittivity, the easier response of that given dielectric to the electric field. So that's for the easier how the dielectric respond to the electric applied will be end with higher value of relative permittivity. So that should be our conclusion in our first topic of discussion, which is dielectric under static condition. So the ending parameter in the discussion is known as dielectric constant. So it's very important part of parameter when we talk about dielectric with regards to applied electric field. Okay, so that's completed. So let's go to the next topic now. So the next topic, so alhamdulillah we have done this part already. So we're going to talk about dielectric boundary condition. That should be the next issue before we end our lecture. Dielectric boundary conditions. Okay, so that should be our topic of discussion. So I'm sure you have seen this idea being proposed before. Remember we talked about conductor free space boundary conditions? Yes, so that discussion is still applicable in our current topic here. So the one that we talk about still can be used in our discussion now. So let's recall how we represent the boundary before, just a flat surface. And now we are going to assume as before the upper region of the boundary denote as region number 1. The bottom region we're going to denote number 2. Since we already mentioned this to be known as dielectric boundary condition, meaning that region number 1 should be a dielectric material, and region number 2 should also a dielectric material. So the way we're going to represent a dielectric now using the parameter that we just talked about, epsilon. So I'm going to denote that to be epsilon 1, and this particular region, bottom region to be epsilon 2. So by seeing this being represented in our diagram, we know that these two regions are having different dielectric material. Okay, so I can represent this epsilon 1 as epsilon R1 epsilon naught. Remember the equation we derived just now, the relative permittivity or dielectric constant of region 1. So this one should be represented as epsilon R2 epsilon naught. So that's how we're going to represent that. Yeah? Epsilon R2, the dielectric constant that we just saw in the table just now. Okay, so what happened to the electric field? Yes, the same thing going to happen to the electric field as what we proposed in the first condition, the first boundary condition, which is the conductor free space. So what we're going to see, the electric field going to be refracted. So this is going to be the scenario of the electric field migrating from one dielectric to the other dielectric. So this is going to be denoted as E region number 2, and this is going to be denoted as E region number 1. And then what we stated before, the conditions at this particular point that appear to be at the boundary going to be known as boundary conditions. Okay, so this boundary condition actually an equation that relating E1 with E2. That should be what this boundary condition do. Yeah, is actually equating how the E1 is related to E2. Where this particular situation is being focused? Yes, at this particular position. And then we have concluded to make this model easy, regardless any boundary that you're going to have in your problem. So we're going to split the boundary condition into two components, because what? Regardless what your boundary, the normal always making angle 90 degrees to the boundary, correct? And the tangential always making angle 0 degree to the boundary. So therefore, we're going to represent the boundary condition into two models. So remember the model that we developed before. Okay, the first model, we call it to be boundary condition number 1. Or we also denote that to be known as normal component. So remember, what should be our equation representing the first boundary condition? Yes, D1n minus D2n will be equal to rho s. Okay, so that should be the first equation that we use to talk about the normal component, and we assume that this particular surface actually filled with rho s, surface charge. And then we propose the second boundary condition. What is it? Anyone still remember? Okay, we call it boundary condition number 2, or sometimes we rephrase that to be tangential component. Tangential component. Anyone can recall how we represent this boundary condition? Yes, E1t must be equal to E2t. So how we represent E1t? So this is our E1t parallel to our surface or our boundary, and this is normal to our boundary E1n. That's what our vector we split into two. Similarly for the E2, the one that parallel to the boundary we denote as E2t, and the one that normal to the boundary we call it as E2n. So how the E2n relate to the E1n? By utilizing this equation. And how the E1t is relating to E2t by utilizing this equation. So with that, alhamdulillah, both tasks that we try to discuss in this session have been completed. So we also have done this term in this discussion. Okay, with that, in this particular video session, I have completed talking about these two main issues pertaining to a material known as dielectric material. Okay, in my next video, inshallah, I'm going to talk about application using the above material in actual engineering application. So that's what we're going to go next in our next discussion. By the way, the topic that we discuss now, inshallah, will come out in your test number 2. So please make sure you do understand about the issue that being discussed, and then we're going to go through the problem of handout number 1 in my next video titled tutorial. So with that, I'm going to end my session with thank you for your attention. Inshallah, we're going to see each other again. Take care. Assalamu alaikum wa rahmatullahi wa barakatuh.